are once again welcome to PSI SSS1 Physics. We want to continue our study of dimensions from where we left off in Lesson 2. In this section, we want to examine 1. The uses of dimensions or dimensional analysis. 2. The limitations of the method of dimensions. By the end of this lesson, you should be able to 1. Use dimensions to determine the units of quantities, to assess equations for correctness and to derive equations. 2. Identify some of the limitations of the method of dimensions, like 1. The method's inability to determine the correctness or otherwise of dimensionless constants, and 2. The inability to determine the exact numerical value of a dimensionless constant in a formula derived using dimensions. We shall discuss the uses of dimensions to 1. Determine the units of quantities. 2. To assess an equation for correctness. 3. To derive simple relationships or equations or to derive physical formulae. And 4. Conversion from one system of units into another different system. Example, power in horsepower to watts. Let's begin by looking at determining units of quantities. Perhaps the simplest use of dimensional analysis is its use to determine the units of quantities. For example, since the dimensions of velocity, acceleration, force are Lt to the power -1, Lt to the power -2, and Mlt to the power -2, respectively, their units are meters per second, meters per second squared, and kilogram meters per second squared, respectively. That is, as shown on your screen, velocity equals Lt raised to the power -1, its unit being meters per second. Acceleration equals Lt to the power -2, its unit being meters per second squared. And force equals Mlt raised to the power -2, its unit being kilogram meters per second squared. The units of many derived quantities can be found in the same way. It is important to note that in certain cases, more common units are used as alternatives to those that are obtained using dimensions. Example, the more common unit of force is a Newton, represented by capital N, instead of kilogram meters per second. Now consider the equation F equals G M1 M2 divided by R squared. In making G the subject of this equation, G would be equal to F R squared divided by M1 M2. We can normally obtain the unit of G, referred to as the universal gravitational constant, by considering the units of force, radius, mass 1, and mass 2. F is a force, R is a distance, and M1 and M2 are masses. Units of G equals units of F R squared divided by M1 M2. This equals N M squared divided by kilogram squared. This equals N M squared per kilogram squared. Let's represent this equation with 1. Or if we use kilogram meters per second squared in place of newtons, we have units of G equals units of F R squared divided by M1 M2. This equals kilogram meter per second squared times meter squared per kilogram squared. This gives us meter cube per second squared per kilogram. Let's represent this with 2. Using dimensions, we can obtain the units of G as follows. Dimensions of G equals dimensions of F R squared divided by M1 M2. This equals M L T raised to the power -2 times L squared divided by M squared. This equals M L T raised to the power -2 L to the power 2 and M to the power -2. This gives us L to the power 3 T to the power -2 M to the power -1. Units of G equals units of L cube T raised to the power -2 M raised to the power -1. This equals M cube per second squared per kilogram. Therefore, we can obtain the units of a quantity by considering the units of the quantities in the relation defining the quantity, or we could use the dimensions of the quantities involved. You can try this work on your own. identify some derived quantities, and the relations or equations that define them. Use these relations to determine the units of the quantities by first obtaining their dimensions. Now, I would also consider the second one, that is assessing equations for their correctness using dimensional analysis or dimensions. As beginners, let me use some examples of equations which are known to be correct. We shall meet these equations in our studies later in SS1. Now, viewers, the equations are 1. V equals U plus AT. 2. V squared equals U squared plus 2AS. 3. S equals UT plus half AT squared. And 4. S equals U plus V all into T divided by 2. Where A equals constant acceleration with which a body moves, U equals initial velocity, V equals final velocity, S equals distance traveled, and T equals time taken. We shall pick any of these equations for illustration. We may deliberately alter some of the equations to make them wrong so that we can find out what information we can obtain about these equations from dimensional analysis. An equation is dimensionally homogeneous or dimensionally valid or simply valid if all the terms on both sides of the equality symbol have the same dimensions. Also, corresponding quantities on each side of the equality symbol must have the same indices. Let us now examine some equations. Let's first consider an equation which is homogeneous and correct. V equals U plus AT. That is LT to the power -1 equals LT to the power -1 plus LT to the power -2 times T. This implies LT to the power -1 equals LT to the power -1 plus LT to the power -1. Thus, all the terms have the same dimensions, LT to the power -1. The equation is thus homogeneous. We also know that the equation is correct. Now, we'll consider an equation which is wrong but homogeneous. V equals 2U plus AT. That is LT to the power -1 would be equal to LT to the power -1 plus LT to the power -2 times T. LT to the power -1 equals LT to the power -1 plus LT to the power -1. Note that 2 is a dimensionless constant. or a mere numerical multiplier. Multiplying u by 2 does not change the dimensions of u, and the equation still remains homogeneous, even though it is wrong. Here it is a dimensionless constant 2 which is wrong. We have deliberately introduced the 2. You can also introduce some dimensionless constants into any of the equations 1 to 4 and see what happens. Now we would also want to consider an equation which is not homogeneous and wrong. Let us make an equation wrong, not by altering or making a dimensionless constant wrong, but by making a variable which has dimensions wrong by altering its power. Let's consider the equation v equals u plus at squared. Here lt to the power minus 1 equals lt to the power minus 1 plus lt to the power minus 2 times t to the power 2. This implies lt to the power minus 1 equals lt to the power minus 1 plus l. Thus, all the terms do not have the same dimensions. The equation is thus not dimensionally homogeneous. We also know that the equation is wrong. What deductions do we make from this? 1. An equation which is not dimensionally homogeneous is a wrong equation, since in any correct equation, each term represents the same quantity. Each term must therefore have the same dimensions. Dimensional homogeneity is a necessary condition for the correctness of an equation. 2. An equation which is dimensionally homogeneous may be correct. An equation in which one or more of the dimensionless constant is wrong will still remain dimensionally homogeneous, but it will be a wrong equation. Dimensional homogeneity is not sufficient condition for the correctness of an equation. 3. In checking an equation for correctness, if it is found not to be homogeneous, it must be ruled out as a wrong equation. If the equation is found to be homogeneous, then it may be correct. The equation has only satisfied the necessary condition, but it may still be wrong. That is, a dimensionally homogeneous equation may be correct or wrong. All correct equations are dimensionally homogeneous. We can depict the information vividly in a Venn diagram as shown on the screen. H represents homogeneous equations. C represents correct equations. The diagram shows that all correct equations are homogeneous, but not all homogeneous equations are correct. This is because an equation in which there are wrong dimensionless constants will be dimensionally homogeneous, but the equation would be wrong. In conclusion, one must note that dimensional homogeneity is a necessary condition for the correctness of an equation, but it is not a sufficient condition. Now, we would consider the use of dimensional analysis to derive equations or physical formulae. This is perhaps the most common use of dimensional analysis. It is best illustrated using examples. Let's consider this example. Suppose it is known that the period t of oscillation of a simple pendulum depends on its length, L, and the acceleration due to gravity, g. It is required to use dimensional analysis to establish the exact relationship given that the dimensionless constant in the relation is 2 pi. We can then proceed as follows. T depends on L and G. T is related by a constant of proportionality, K, to L and G. Thus, this can be written as T equals K, which is a constant of proportionality, L raised to the power X, and G raised to the power Y. K is a dimensionless constant, and it is given as 2 pi. Now, taking dimensions on both sides of the equation, we have T equals L to the power X times LT to the power minus 2, all into brackets Y. Here we ignored K because it's a dimensionless constant. Now let's try to expand the equation. We have T equals L to the power X times L to the power Y times T to the power minus 2y. By combining like terms, we would have T equals L to the power X plus Y times T to the power minus 2y. For dimensional homogeneity, the index of a given fundamental quantity should be the same on both sides of the equation. Thus, equating indices of T such that 1 equals minus 2y, equation 1, index of T on the left hand side equals 1 and index of T on the right hand side equals negative 2y. L will be such that 0 equals x plus y. Let's represent this with 2. There is no L on the left hand side of the equation, and therefore the index of L on the left hand side equals 0. From 1, y will be equal to negative half. Putting y equals negative half in 2 gives x equals half. Now from A, T equals K, L raised to the power X, and J to the power Y. K equals 2 pi, that is already given. x equals half and y equals negative half. Substituting this into the equation A, we would get t equals 2 pi L raised to the power half j raised to the power negative half. Rewriting this, t would be equal to 2 pi L raised to the power half divided by j raised to the power half. This implies that t equals 2 pi square root of L divided by j. Note that when any number is raised to the power of half, we obtain its square root. Take this question so that you can solve it on your own. The velocity v of a transverse wave through a string is known to depend on the tension T in the string and on the linear density or mass per unit length mu of the string. Use the method of dimensions to establish the exact relationship, assuming that the dimensionless constant is unity or 1. This hint would help you. 1. T here is tension, not period, and is thus a force with dimensions capital M, capital L, capital T to the power minus 2, and mu equals mass divided by length. This implies mu equals capital M, capital L raised to the power minus 1. 2. You are expected to obtain V equals square root of T divided by mu as your final answer. Now let's consider some limitations of dimensional analysis. There are a number of limitations, but the most outstanding are: 1. In the use of the method to assess equations for correctness, it can't identify dimensionally homogeneous equations, which are wrong. This is because if a dimensionless constant is wrong, the method cannot tell us. In the use of the method to derive equations, the method cannot give us the value of the dimensionless constants, which thus must be obtained from another branch of physics and given to us for use here. If this constant is wrong, the method cannot tell us. In this lesson, we've seen that dimensional analysis has a number of uses. It can be used to determine units of quantities, find out whether an equation is correct or not, and derive equations or formulae. However, the method has also been found to have limitations, hinging on its inability to determine or trace a wrong dimensionless constant. This notwithstanding, the method has been found to be interesting. This is where we end today's lesson. I hope you've enjoyed it. Till we meet again for our next lesson, keep on learning physics. Bye for now.